this systematic review, I'm really focusing on neonatal survival. So more specifically, I'm focusing on how these maternal effects actually senesce. And there is much sort of anecdotal evidence to suggest that increased maternal age decreases neonatal survival. However, current theories of aging actually ignore potential differences and evolutionary pressures that are exerted on reproductive traits such as neonatal survival, number of offspring, and offspring size. And current evolutionary theories of aging actually can't explain maternal effect senescence and its divergence from fertility senescence. So this systematic review is essentially testing between two main evolutionary models of maternal effect senescence. And they make differing predictions about how the strength of selection for the maternal effects on neonatal survival changes with age. So you've got this original Hamilton-based theory, which predicts that this should follow from the female age distribution, or the novel evolutionary theory that Jacob Moorhead and Dan Nussey have created, which predicts it should follow from the maternal age distribution. So just to start with by saying that they've actually released a paper this year which really explains it in a hell of a lot more detail than I will, but so I urge you to actually check this out if you want to look at equations and derivations. But for now, what I'm sort of looking at is the difference between the old theory and the new theory. So in both cases, neonatal survival at offspring age 0 at maternal age X for the old theory is proportional to Px, which is equal to cumulative survival. However, this new theory basically explains neonatal survival is proportional to Mx, which is equal to the product of age-specific fecundity, so Mx, and cumulative survival. And we know that Lx decreases with increasing age. But these models actually, their predictions differ when female fecundity changes with age, and there's two main sort of scenarios when this actually occurs. The first one is when you have variable age of first reproduction. So neonatal survival can actually increase with maternal age, and you see this in quite a lot of seabird species, for instance, such as the wandering albatross. And also when the second scenario is when you actually get reproductive senescence, so when fecundity changes with age. So from these theoretical models, we have hoped to answer several questions with this systematic review. Essentially, is maternal effect senescence widespread? Is neonatal survival actually affected by the age of the mother? And if so, how does it evolve? Is it a form of reproductive senescence, or is it something more? Is it this novel evolutionary theory that Jacob and Dan created? So which evolutionary model best fits the observed pattern we see? So how I went about this was essentially following standard systematic review or meta-analytical review flowchart. And you start with your search criteria, which is relevant to the questions you're answering. So this was, for my work, was neonatal survival and anything to do with age distribution of females or age distribution of mothers. And essentially I put these all into Web of Knowledge and Scopus, and it churned out 9,000 papers. I removed these duplicates, and there was about 7,000 left over, and I rejected these papers based on their title and abstract and the relevant information or the irrelevant information that they contained. I also had a rejection criteria, so anything to do with humans, male age, male care, and highly used social animals, I rejected. So then this sort of led to about 800 papers being left over, and I essentially read all these papers to see if they had the relative parameters I needed for analysis, and also if they graphically described this, so I could actually extract the data. So in the end, I was actually left with 35 papers that were accepted, and these covered 32 different species, ranging from cheetahs, jaguars, and mammals, several bird species, and also a fair number of insect species, from Drosophila littoralis to stem boll weevils, for instance. So how did I go about analyzing this? Well, essentially, I extracted the data from these accepted papers using a graph digitizer, and it's really simple. You upload a JPEG image of the graph or bar chart, you specify the axes, and then you specify the axes, and then you plot the data points and you get the data out of it. I then ran 4 binomial GLM models with probit link function for each of the species, so each of the 32 species. And the explanatory variables for neonatal survival were related to the questions we were wanting to answer. So we had, is maternal effect senescence widespread? Does aging actually affect neonatal survival? So that was the age-independent model and the age-dependent model. Then we also asked which evolutionary model best fits the observed pattern. So that was the original theory or the novel theory. In several cases, the organism was actually placed on multiple different substrates or experimented in different environments. We actually controlled for the effect of treatment. At the end of this, I just recorded the log likelihoods and effect sizes for all the 4 models. And essentially, these are just some histograms sort of showing the effect size distributions for each of the models. So you have the original model here, you have the novel model here, and you have the age-dependent model here. And in several cases, with these evolution models where it actually goes negative, which is, I think the formatting is skewed up a bit because you can actually see it. Where it goes negative, this is actually negative senescence. And when it's actually positive here, this is negative senescence. But that's for the age-dependent model. Well, I'll come back to that in a second. So essentially what I did was I got these species-specific log likelihood totals and effect sizes. I totaled these log likelihoods and effect sizes across all species, and I calculated, along with the number of parameters, a composite AIC for the age-independent model, the age-dependent model, and the 2 evolutionary models to enable comparison. So what did I end up finding? Well, the first question we wanted to answer is maternal effect senescence widespread? Is neonatal survival actually affected by the age of the mother? And across all species, we actually found that the age-dependent model was the better fitting. Also, just so if you don't know, a lower AIC is a better fit. So we found that the age-dependent model was a better explanation for neonatal survival, which is great, because then we can delve a little bit deeper, because we also wanted to ask whether we wanted to analyze the relative frequencies of these positive and negative maternal effect senescences that we saw in the effect sizes with a simple sign test. And we were essentially asking whether maternal effect senescence was widespread. And the null hypothesis was essentially there is an equal chance of finding positive and negative maternal effect senescence. And when we looked at it across all the 32 species, we actually found that there was an equal chance of finding positive and negative maternal effect senescence. And then I broke it down into natural populations and lab-based populations, and natural populations with conspicuous maternal care. And we also couldn't reject this null hypothesis. So there was equal chance of positive and negative senescence. However, when we looked at lab-based species without this post-action care, we actually found that we could reject this null hypothesis, because in the lab they actually showed there was a strong evidence for maternal effect senescence. So when we did see this maternal effect senescence, we then wanted to ask which evolution model better fit the observed pattern. And running for all the species that showed maternal effect senescence, we actually showed that the original model was a better fit. So the age distribution of females was a better fit. But when I looked into a little bit more, I removed any laboratory species and only included those that actually were natural populations with conspicuous maternal care. And we actually found that those natural populations where maternal effect senescence was occurring, we actually found that it actually favoured the age distribution of mothers rather than the age distribution of females. So we can kind of say that in total it was favouring the female age distribution, but when we actually look at more natural populations, they were focusing on it actually was better explained by the age distribution of mothers. And one reason for this could be actually because the lab populations showed demography that is quite artificial, so it may not be actually appropriate for this analysis. So in summary, we kind of showed with this analysis, because it's ongoing, it's going to improve and it's going to change. We showed so far that there's limited evidence for maternal effect senescence. However, there is strong evidence for it in the lab. And when it does occur, it's better explained by age distribution of mothers when we're looking at natural populations. So the new model is actually a better fit when we're looking at natural populations with conspicuous maternal care. But female age distribution is actually a better explanation for laboratory populations when we're looking at laboratory population maternal effect senescence. So the next steps that I'm going to be doing with this work is essentially I'm going to be widening my sample size and trying to look at more natural populations to see if the age distribution of mothers is still a good fit. I'm also going to solicit raw data from investigators, and I know I've asked a couple of people already at this conference. One thing I didn't do in previous analysis, I didn't correct for phylogenies, and this is something that I'm looking to do in the coming future analyses. And lastly, the other thing I was going to do was include other life history traits. So we looked at post-hatching care, so presence or absence of conspicuous maternal care, post-hatching care. And so I'm also going to look at other life history traits, such as maximum longevity and body size, and see if this changes the fit of the evolution models. So with that, I'd like to thank my funding bodies, East Bio, BBSRC, Jacob Morad for his assistance, and the University of Edinburgh. Thanks.
So demographers probably have the richest data set with humans, so why did you exclude them?
Just because they kind of represented, they were too complex, essentially. We wanted just to use species where they didn't have the complex social system in place. That answers your question.
So maybe you said this and I missed it, but what were the 35 species? Were they all mammals?
No, oh sorry, did I not explain that? Okay.
I might have missed it.
So it was 35 papers, there were 32 species, and it was kind of a half and half split between, there was about 14 mammal species, ranging from cheetahs, jaguars, seals, soaceae, and there was also a whole host of other invertebrates and bird species as well. So invertebrates were Drosophila littoralis, stem boll weevils, I can't remember all of them off the top of my head, but there was quite a mixture.
Not having seen the distribution of the data, it seems likely that the lab wild comparison is heavily confounded by body size and phylogenetic effects, thinking that the lab species are more biased towards invertebrates and smaller vertebrates. Also, the lab populations are likely to have females reproducing later in life than field populations because of natural mortality. So I guess it's just sort of a caution about attributing differences between lab and field to lab versus field rather than.
That's definitely something we've been thinking. We've noted, yeah. Thanks.
Along those lines, do you think there's a possible genetic influence in lab populations versus natural populations? A lot of lab populations are very red, so very low in genetic diversity.
I don't know. Do I have enough time to answer that?
Yeah, this transitions.
Okay. I've not really thought about that. Can I think about it and get back to you?